Oh, all right. So this is lecture 9 of 124104, Physics 1A. In this lecture, we will talk about conservation of energy, coming off of last week's, yesterday's lecture, where we talked about energy, work, and power. So we defined what work is, energy, and power in our lecture yesterday. And we left off from this example, and we didn't have time to look at the solution of this. So let's start this lecture by looking at how to solve this problem. A pump lifts 21 kilograms of water per minute through a height of 3.5 or 3.50 meters. And you want to find the minimum output rating for the pump in order for it to lift this much water. So if you visualize the problem, you have and some rumbling. I don't know what's going on. Please be kind. All right, so you have here 21 kilograms of water. You want to lift it up to a certain height, 3.50 meters. Yeah. So of course you'll need to exert a force. There's some dinosaur up there. You need to exert some force. So the pump needs to have this lift force in order to lift this mass up a height of 3.50 meters. And the problem says it should lift that much water in 1 minute. So the time is 60 seconds. Okay, we want power. Power is defined as work divided by time, right? We know time is easy, it's given. Now we have to figure out how much work the pump does in lifting this much water to a certain height. And we learned that work is equal to force times the distance traveled times cosine theta over time. So I've just expanded the equation using the definition for work. Now the question now is, what is this force F? So this force F is the force to lift the water to the given height, 3.50 meters. And the amount of lift that the pump needs to give should be equal to the water's weight, right? So that if the amount of lift is equal to the water's weight, then the water will be lifted up. Does that make sense? Yeah. So the force to lift water should be equal to the water's weight. In other words, force should be equal to mass times gravitational acceleration. Mass being the mass of the water you want to lift, and G, of course, 9.8 meters per second squared. So then we have everything. I'll just use this space. Therefore, power will be equal to mg d cosine theta over t, where theta, what will be theta in this case? So the lift force is upwards and the displacement is also upwards. So that means the angle between the two vectors involved in the definition of work is equal to 0. They're in the same direction, and hence theta is equal to 0. Yeah. So therefore, power will just be 21 times 9.8 times 3.5. Yeah, and cosine 0 is 1. But I'll just write it down just to be sure. And then time is 60 seconds. This should give you a power of 12.0 watts as shown in this answer here. All right. Okay, the key here is just realizing that the force needed to lift the water should be equal to the weight of the water that needs to be lifted. Yeah. All right. And so if you've downloaded the lecture slides from Stream, there is a revision problem there, which talks about the elevator having this mass 1,200 kilograms and containing people with a total mass of 1,000 kilograms. And the elevator rises 80 meters in 20 seconds. And the revision problem asks you to find the work that the elevator does to lift of course, the elevator and the people together, and the elevator's power. So it's exactly the same principle as the example we looked at with the water being lifted by the pump. Okay, so you do exactly the same solution with the same solution there, and I'll just write down the answers. I'll just write down the answers here. First, you were asked to find the work and then the power. The work is 1.7 times 10 to the 6 joules, and the corresponding power is 8.6 times 10 to the 4 watts. Right, but I leave it up to you to work out the solutions, because as I've mentioned, the principle is exactly the same as the example we looked at earlier. All right, sounds okay. Good. All right, so so yesterday we defined energy. It's what allows us to do work, and we've identified two kinds of energies: kinetic energy and potential energy. Yesterday we talked about kinetic energy being the energy associated with motion. So there is a speed involved in kinetic energy. So today we will talk about what potential energy is. And there are two kinds of potential energies. We'll consider elastic potential energy and gravitational potential energy. So let's first look at elastic potential energy. So potential energy in general, it's the measure of the potential. That's why it's called potential energy. It's the measure of the potential or possibility to do work. Right, so with elastic potential energy, as illustrated there. So for example, I have a bow and arrow here. Okay, when I stretch the elastic spring, I pull the elastic spring and pull the arrow backwards, I do work, right? So initially the arrow is in this position, it's not moving. If I pull it, I essentially do work on the arrow, right? It moved, so there's some work. The energy I used to do work in pulling this arrow is stored as elastic potential energy in this elastic band. So that this elastic band will now have the potential to do work. Okay. If I let go of the arrow, the elastic band will now exert a force on the arrow, pushing it forwards, and therefore it will have done work. Should have done it. Go closer or something, right? So yeah, the equation for elastic potential energy is shown here. Yeah, it depends on the length of the compression or stretch of the elastic band, or if it's a spring, you also have elastic potential energy if you're stretching a spring or compressing a spring. X in the equation for elastic potential energy is the length of compression or stretch, and K is some constant called the spring constant. So the spring constant, this is a property of the spring or the elastic band, which describes how stiff the spring is. So the stiffer the spring is, the bigger the spring constant is. So yeah, elastic potential energy, it's essentially energy that's stored in something that's elastic, like a spring or an elastic band. And the stored potential energy gives the band or the spring the possibility or the potential to do work. Right? For gravitational potential energy, say I have a ball, and initially the ball is on the surface. Let's use the surface of the table as the reference height. It's initially at a 0 reference height. if I take the ball and I lift it up to some elevation h, then I would have done work in lifting the ball up, right? Because I exerted a force and there's some displacement. And so therefore I did work in lifting the ball up to this certain elevation or height h. The energy I used in doing work to lift this ball up is stored as gravitational potential energy, so that the gravitational force will then have the potential or possibility to do work on the ball. Once I let go of the ball, the gravitational force will then will then pull the ball downwards. The ball will travel a certain height d, and therefore the gravitational force would have done work in pulling the ball down to the original elevation. Right? So gravitational potential energy is then given by this equation. It's associated with the object's weight and position h. So position h, this is the vertical elevation with respect to a reference. So if you wanted to increase the gravitational potential energy, we can increase the mass or the elevation, or if we're just looking at the same object with the same mass, then we can increase the gravitational and potential energy by increasing the elevation of the object. Right, so let's look at these scenarios. Yeah, so for example, you have the ball. Initially, it's on the ground, and say let's use the ground as the reference height. So we put height equals 0 to be the ground, and we lift the ball up to a certain height HA. The ball will now have a gravitational potential energy of mg times the height HA, right? Okay, but there's nothing stopping us from choosing any other reference points or other reference heights. There's the reference position that you choose is arbitrary. There's nothing stopping you from choosing, say, this certain height to be your reference point, and so you assign h equals 0 to be this reference height. And in this case, you then measure the elevation relative to your chosen reference height. So say the elevation is HB, then the gravitational potential energy will be different, right? Because the elevation is different from when you use the ground as your reference height. So this in the second case, the gravitational potential energy is mg times the height b. Now, the gravitational potential energy can then be positive, negative, or 0. Okay. So in this case, the gravitational potential energy is positive. When do you think will it be negative? Yeah. If I put my reference height above the object, so the object is below the reference height, say that is height hc, then the gravitational potential energy will be negative. And of course, it's 0 if you put the objects at the chosen reference height. Or yeah. So, but what I wanted to show and demonstrate is that gravitational potential energy is not unique. Yeah, because we are free to choose any reference height to use. And because gravitational potential energy itself is not unique, the change in gravitational potential energy will be the more useful quantity, right? It's delta gravitational potential energy that's useful instead of U itself that is useful. So the delta U already accounts for the reference height. All right, and in fact, it's this change in potential energy that is equal to work. Okay. All right, with the, so the negative sign here means that as work is being done, the gravitational potential energy should decrease. So going back to the demonstration with the bow and arrow, I'll try to make a better job. Okay, so as we said earlier, when I pull the arrow, I'm storing elastic potential energy on the band. Okay, when I let go, then the band will do work on the arrow. Oh, still. But as work is being done to push the arrow forwards, the elastic potential energy decreases. Right? The elastic band goes back to its unstretched position, and therefore the elastic potential energy stored in the band decreases as work is done. And that's why you have this negative sign here. Okay? As work is done, the potential energy needs to decrease. Cool. Right. So we've the change in potential energy is equal to work, negative change. So work done, let's look at this, what we call conservative force. First, let's look at what the conservative force is in relation to work, and then later on, let's define what conservative force is. So work done by conservative force is independent of the path taken. Gravitational potential energy is an example of a gravitational force is an example of a conservative force. So say you have these three scenarios here. You have a ball and you lift it up to the same height, 3 meters. Okay. But in each of these three scenarios, you use a different path. In the first case, you just directly lift the ball up to 3 meters of elevation. In the second scenario, you maybe pull it through an inclined plane. And in the third scenario, you go through the steps here. If we want to find the work done in lifting the ball up to the certain height h, we can use this principle, work is equal to negative change in potential energy, to figure out how much work was done in lifting the ball up this certain height, 3 meters. Right? How much work is done. So we can say delta U mg delta h. Okay, so we can use this as our reference height. We can use this as our final height, 3 meters, so that the change in potential energy of the ball, let's say it's a 10 Newton ball, so the weight of the ball is 10 Newtons, meaning mg is equal to 10 Newtons. So the change in potential energy in the ball when it goes from the ground, which we've chosen to be the reference height, to 3 meters will be 10 times 330 joules. Right. So therefore, notice how in the equation for the change in potential energy, it's just the height that matters. It doesn't matter which way you used in lifting the ball up. As long as the final height of the ball is the same, then in each of these three scenarios, the change in potential energy of the ball will be the same. And therefore, the work done will also be the same in each of the scenarios. Yeah. Right. So therefore, gravitational force is an example of a conservative force because the work done against the gravitational pull is the same regardless of the path taken.
What is the risk the opposite of this case, because you're putting the changes into it, when it's negative when it's losing its potential?
Oh yeah, no, that's a good point. So we're just sort of looking at it overall with work being related to potential energy. You're right that in lifting it up, we're putting in energy, and when we let go, we're releasing energy. But this is a general definition that tells us that the the relationship between work and potential energy are inverse, so that when potential energy decreases, the work increases. But we don't sort of separate the change in potential. It's the overall change in potential energy that we're considering. Okay. If we consider just work, if we just consider work, then it will matter whether it's negative, positive, or zero. So we'll look at this example here when work is negative, positive, or zero. But for a conservative force, the work done in moving around a closed path should be zero. It's easy to, we can analyze this using this definition, right? If we write this down, expand this in terms of gravitational potential energy, for example, then work will be equal to mg times delta H, okay? Meaning the change in potential energy is due to the change in height. But if you go back to your original position, that means your final height is equal to your initial height. So the change in height will be zero. And therefore, in a closed path where you go back to your original height, the work should be zero as well. Work should be zero if you go back to your original position or height. Okay, to prove this, to prove that the work done around a closed path should be zero if the force is conservative, let's consider throwing a mass up a height h. So we have the ground here as the reference point. There's gravitational pull downwards. Okay, you have this object that's thrown up a certain height h and then goes back down. Okay, if we work out the work done by gravity for the round trip, in going up, the work done by gravity will be negative mgh, right? Why? Remember, work is equal to Fd cosine theta. Okay. It's the work done by gravity, therefore gravitational force due to gravity is always downwards. On the way up, the displacement is upwards. And so on the way up, the direction of the gravitational force and the displacement is opposite, meaning theta is 180 degrees. Therefore, on the way up, it should be negative work done by gravity. Do you agree? Makes sense? All right, whereas on the way down, the work done by gravity will be positive. Again, still the gravitational pull is downwards, but the ball is also going downwards. So the displacement on the way down is in the same direction as the gravitational pull, gravitational force. Hence, theta is equal to 0, cosine 0 is equal to positive 1. Right, so the work done is equal to mgh. So if we look at the total work done, we're just adding the individual works. This will be 0. So if you have an object that goes through a closed path, meaning it goes back to its original reference position, then the work done by a conservative force should be 0. All right. Okay, now, so we've learned that the work is equal to negative change in potential energy. We also learned in our lecture yesterday that work is equal to the change in kinetic energy. Yeah, yesterday we learned about this, that when the object, if the object starts from rest and goes and moves to a certain speed, then the force would have done work in moving this object, and therefore the work is the change in kinetic energy. So these are the same. They're both talking about work, that the total work, so we can equate the two. change in kinetic energy should therefore be equal to the negative change in potential energy. Which again, if you look at the bow and arrow demonstration, as the potential energy of the elastic band decreases, the arrow moves and has this kinetic energy, right? So the potential energy in that case was converted to kinetic energy. I just rearranged this equation into a form where the right-hand side is equal to 0. Okay, and I rearrange it this way because it's the common form for what we call the law of conservation of energy. So the law of conservation of energy says that energy cannot be created or destroyed. It's just transformed from one form to another. In this case, the potential energy U is being transformed to the kinetic energy K. And because you have transformation of energy, you'll have a change in potential energy and a change in kinetic energy. Right?
That's assuming that it's all translated into the kinetic. You don't have any dissipation.
Yes, we will get to, like, this is assuming there's no friction in essence. So friction will dissipate energy, and we'll get to the role of friction later on. So at this point, yes, we're still assuming negligible friction. Good point. Okay, right. So let me expand this equation. Right, change delta, the Greek symbol delta or triangle means change, meaning final minus initial. So I just expand delta K as final kinetic minus initial kinetic energy. I do the same thing for the change in potential energy, final minus initial potential energy, right? And then I want to collect all the initial terms on one side and all the final terms on the other side. Right, so I have initial kinetic plus initial potential energies should be equal to the final kinetic plus final potential energy. Okay. I want to expand the equation further by using the definitions that we learned for kinetic energy and potential energies. So we learned two potential energies, gravitational potential energy and elastic potential energy. So then I have this expanded equation, right, that involves the speeds of the objects, initial and final speeds of the object, initial and final position of the object, and if there's a spring or an elastic band, it also considers the elasticity, the spring constant, or how stiff the spring is and how much you've stretched the spring. But this expanded equation just all came from this idea that energy is conserved, so that potential energy transforms to kinetic energy, or kinetic energy transforms to potential energy. But this conservation of energy is a very powerful tool, and it's quite simple because we're dealing with only scalar quantities, right? We're not talking about vectors. We're just talking about speeds or initial and final positions. And this equation will allow us to calculate, for example, final speed or displacement or final position. And so we'll look at some examples later on, right? But let me also just point out that when we say energy is conserved, that also means that the total energy in the system should not change, right? So when we say energy is conserved, the total energy should remain the same. It's just being converted or transformed from one form to the other, from potential energy to kinetic energy or vice versa, right? Okay, and so if total energy should remain the same, the total energy should then be a combination of kinetic energy and potential energy. Again, we're assuming frictionless system. There's no dissipation of energy here. Right? Okay, so let's, as I've said, any increase in potential energy will result to a decrease in kinetic energy so that the total energy is the same. So let's look at this conceptual example to see the relationship between total energy. So E is the total energy, K kinetic energy, U potential energy. So let's look at the scenario where you have Homer Simpson in a burning building. So he went up to the roof and he's now trying to decide whether he'll jump down to the ground or not. Not a good idea. Please don't try this. Unless, of course, there's a firefighter down here telling you to jump because there's a trampoline that will break your fall. All right, so let's just consider that he's at a certain height, H. Okay, and he's trying to decide. So he's standing still, thinking, contemplating whether he'll jump or not. In that condition, what can you say about his kinetic energy and his potential energy? Let's assume that, let's take this as a reference height, the ground to be a reference height, and this is some height H. So what can you say about his kinetic energy and potential energy at this point? Zero kinetic, he's not moving, he's just thinking. How about his potential energy? Should be some maximum value, right? Okay, so his potential energy will be some maximum value. He has zero kinetic energy. His total energy is purely potential energy, right? Hey, what if, he's crazy, so he jumps. Okay, and at this point, 1/3 down the top of the roof, what can you say about his energies, kinetic, potential, and total energies? 1/3. Yeah, if this is 1/3 the height, then his potential energy would have decreased by 1/3 of the maximum, right? Where did this decrease in potential energy go? It will go to the increase in his kinetic energy. Because as he's moving down, he will have some speed, right? Remember that kinetic energy, mv squared, potential energy is mgh, right? So since he jumped, he'll be moving, he'll have a certain speed. His total energy should still be the same as before. Halfway through, okay, and you probably start to see a pattern here. Potential energy will be half. Where did that half of the original potential energy go? It went to kinetic energy. So you'll see here as we think about it, right? When we learn about free fall, an object freely falling will increase its speed as it falls down, right? And since his speed increases, his kinetic energy should increase. Okay? And since his height is now lower compared to before, his potential energy should decrease. But his total energy would still be the same. Right? Energy is conserved. 2/3 down. Okay, you see this pattern here. And finally, when he hits the ground, he would have reached a height of 0. So his potential energy is 0. He would be traveling at maximum speed. Right? His kinetic energy will be maximum and his total energy will be purely kinetic. Right? Yeah.
I know this isn't really relevant because of the number in the system, but what would actually happen when you hit the ground to change? Would it go to like friction or like stampede or something?
Yes, so it will be, it has to be transformed to some form of energy. It just cannot disappear. So even if there's friction and other kinds, even if it's not an ideal system, the total energy would still be the same. So it will be, you hear a sound or there's some heat generated or, explode his body. Goes into the energy to explode his body or something. It has to go somewhere. The energy has to go somewhere. All right. Okay, good. So this is the conceptual, visualization of what's happening to the energy. Now let's look at a numerical problem to apply the conservation of energy. And we'll see, so this problem is a free fall problem, which is, we've learned about free fall before, and we've learned how to use kinematic equations to solve for free fall. But this time we'll use conservation of energy. So you have a skydiver with a mass of 70 kilograms. The skydiver is 400 meters up. He or she is just about to jump off the plane. If his or her parachute fails, how fast will this skydiver be going when he or she hits the ground? On the way to answering the question how fast, you'll also consider his gravitational potential energy, and as a follow-up, his or her kinetic energy on the ground. Okay, right. So this is the equation for conservation of energy that we've seen. The total initial energy consisting of kinetic and potential energies should be equal to the total final energy consisting of kinetic and potential energies. Right? Okay, we have to expand this equation in order to explicitly see how the speeds are involved in the conservation of energy, right? Right. So we can simplify this expanded conservation of energy equation. So the diver is just about to jump. So we can say that the initial velocity, initial speed is 0. Let's just talk about speeds because energy is just a scalar quantity. And then we can use, say this is, I'll just draw. I'm a terrible drawer, so I'll just represent things as dots. So say this is the skydiver. Let's just take this to be initial height to be some 400 meters. And let's say final height is equal to 0, hitting the ground. So we can say that the final height is equal to 0 and the initial speed is equal to 0. So we can then simplify the expanded conservation of energy equation by, this will be 0 and the final height will be 0. Hence, we only are now left with these two terms that involve the initial height and the final speed. We rearrange this equation because we want the final speed. That will give a square root of 2ghi, 88.5 meters per second. If you want to go the kinematic equations route and use, free fall, the concepts of free fall, you can also do that. There's nothing stopping you. I will definitely not stop you from using kinematic equations. You'll find that this is the kinematic equation that's most sensible to use because you don't know the time, and all the other kinematic equations will require the time. Right. So using this equation here, rearranging it for VF, of course, VI is also 0. because it's the same scenario of jumping up, then you also see you'll arrive at the same equation, negative g times negative delta x. Yeah. You'll have, yeah, with kinematic equations, we learned it's in vertical fall, you have to use negative g because acceleration is downwards, but also your displacement is downwards, so you have negative. But you can compare these two equations, they're the same essentially, and so it will still give you the same answer for final velocity. But I think for me personally, the kinematic, the conservation of energy is easier to remember because it's just final is equal to initial energies rather than remembering all of the kinematic equations. And then once we know the final speed, we can then find the kinetic energy on the ground when the skydiver hits the ground, using, of course, the final velocity, final speed in this v squared. And don't forget, there's a square, so square your speeds to get the kinetic energy. All right. Okay, to see how powerful the conservation of energy equations are, let's look at this object sliding down an inclined plane. We want to determine the block speed at the bottom of the plane. The elevation of this frictionless incline is 3 meters. Okay, so you have the block sliding down there, and we want to find the final speed here. Okay, we can again say that this is the initial height, 3 meters, and we can take this to be the final height, 0 meters, right? If we use conservation of energy, okay, yeah, some symbols missing, right? Total initial energy consisting of kinetic and potential energy should be the same as the final energy consisting of kinetic and potential energies. And again, expanding the kinetic and potential energy definitions, we have this equation. If we, yeah, I just instantly put, this is of course mghf. Okay? So we put hf to be 0, so we can, yeah, so I've substituted 0 there. And if the block, and then I rearrange. But if the block starts from rest, then we can also put VI to be 0, and we have the expression for VF. And we can find VF easily 7.7 meters per second.
Won't that be in vertical direction? So the velocity.
This one.
We're saying that it's down in that speed, so we're saying what's the speed?
It says the speed along the diagonal, because if you were to solve this using Newton's laws of motion, you will anyway assign this to be your positive x, and this will be your positive y. And so you will find the acceleration along the incline, right? And once you find the acceleration along the incline using the free body diagrams and Newton's second law of motion, you can then find the velocity along the incline by using initial velocity is equal to 0, and you have to know the time for which the block slid down the incline. So the direction for both scenarios will be still along the incline. And we didn't have to get the horizontal and vertical components, because in this case, we assigned the x-axis to be along the incline. There's, of course, nothing stopping us from assigning our x and y axis to be this way. But in this case, we then have to get the final acceleration and final speed will be this diagonal, and so we have to deal with components as well. But this is a more complicated way of arriving at the same thing. Cool. All right. And finally, this friction. So we've been talking about conservation of energy without friction. Now, what happens if there's friction? So as Billy said earlier, friction dissipates energy. So it has to then, if we include friction, then the total energy, so remember E, this is total energy. Okay. Aside from, so total energy will then be a combination of kinetic and potential energies, and we should also consider the work done by friction. Right. Just friction essentially transforms your energy, your kinetic or potential energy into thermal energy. Okay. So still energy is conserved, the total energy is the same. It's just that the energies are transformed to a different form. So friction transforms the kinetic or potential energy to thermal energy. Okay. Right. So any increase in friction, in the work done by friction, will result to a decrease in kinetic energy or potential energy. And this is why friction slows things down, right? Because as something slides across a rough surface, friction will do work in stopping this moving object. Okay? And as a result of the work done by friction, the kinetic energy needs to decrease. And so this object will slow down eventually to a stop. Right. Friction is then an example of a non-conservative force. Okay. So a non-conservative force will dissipate energy, mechanical energy, and convert it into something else. So this table here just summarizes the difference between a conservative force like gravitational force or elastic force to frictional force. The main difference, if is noticed here, the work done, it depends on the path for a non-conservative force, whereas for a conservative force, it's independent of the path. If you think about, if you drag something across a rough surface, it matters whether you drag it across a long path or a short path, right? You drag it along a long path, friction will be able to dissipate more energy, mechanical energy into heat, whereas for gravitational force, it doesn't matter whether you just lift it directly up or through a stair or ramp. Okay, any question about conservation of energy or potential energy or work? Okay, if there are no questions, tomorrow's workshop is already available on stream, so you're free to download that and start working on the problems. Otherwise, I'll see you tomorrow in the workshop, and have a good day, everyone.